Hi, everyone, and welcome to Module 1 of Course 1 of Healthcare Data Analysis. The goal of this course is to demonstrate how statistics can be used to answer questions that arise in healthcare. Over the next 6 weeks, you will learn a variety of statistical techniques that you can add to your toolbox of methods for approaching questions about healthcare data. This week's topic is data itself. We are going to talk about different types of data and ways we can describe and summarize data. Every workplace generates large amounts of data, and that is especially true in healthcare. The trick to analyzing a project is to understand what kind of data you have at hand and to know methods of digesting and presenting the data. This week's topic should help you to start to make sense of the mountain of data available and set the stage for you to be able to analyze data in order to help you answer all kinds of questions. Most people think of data analysis as having to do with lots and lots of statistics. And while that is true to some degree, at the most basic level, data analysis is like doing a bit of detective work. As the person who is given a set of data to analyze, your job is to find patterns among all the information. Once you have found a few patterns, this can often lead to defining trends, and you can start to organize the data to help you answer all kinds of different questions. When beginning a data analysis project, the most important thing you can do is follow a process. It is helpful if the process is the same, regardless of the amount of data you have, the format that the data is in, or the type of data it is. Following a process allows you to track what you've done and what you still need to do. It helps you to support your conclusions and decisions, and makes it easy for you to explain your analysis to someone else. This week, we are going to introduce the 4 basic steps of a good data analysis plan. They are 1. Define, 2. Organize, 3. Evaluate, and 4. Decide. Step 1 was define. Define in the data analysis sense means getting a good understanding of what the problem or issue is that you are being asked to solve. This includes creating a question to answer. It may be that you need to help understand if patient care ratings went up compared to last year, or that you need to find out if there's a trend developing in the length of time that meeting rooms are booked for on a daily basis. Defining a problem doesn't stop at just knowing what it is you are being asked to solve. You also need to understand what types of data you may need to help in finding a solution. Knowing what data are available and how to access it is an important first step in good data analysis. The second step is to organize the available data in such a way as to facilitate analysis. This step includes reviewing the project questions to make sure that you have the data necessary to complete the project, reviewing the problem with stakeholders, and managing the data. Data management may be as simple as sorting the data from smallest value to largest, or vice versa. Or you may need to create new variables out of existing data, such as calculating the body mass index using variables for height and weight. Once you have your data organized, you next want to evaluate the data. The process of evaluating the data may include providing summaries and graphs of the data. Essentially, this is the step where you identify patterns in the data that are relevant to your project. Descriptive statistics, which we will introduce in this module, provide a good method for evaluating the data. The final step is to make a decision about what the data are telling us. For instance, suppose your project involved answering whether men or women are more likely to suffer from heart disease. This is a step where you would make that conclusion based off your evaluation in the previous step. The criteria for making a decision may be as simple as looking at raw numbers, or may use advanced statistical methods. Now that we have a general guideline for approaching a research question, we can continue on towards defining data. Before we do that, however, we need to understand 2 terms, variable and data. Put simply, a variable is anything that can take on different values for different observations. So for instance, age is a variable because one patient may be 35 and the next may be 60. The different values that a variable can take on are referred to as the levels of a variable. As you may guess, the vast majority of constructs, ideas, or things are actually variables. Data may be comprised of several variables. For example, a file on a patient may contain the variables of their residence, age, gender, blood pressure, height, weight, etc. Data are made up of several observations of a variable or multiple variables. If you look at the age of 10 patients, you would have data from these participants on the variable of age. Variables may be broadly categorized as being either quantitative or qualitative. Quantitative variables are probably what you think of when you picture data. Variables are quantitative if there is a numeric difference between levels of a variable. For example, going back to the age topic from just a minute ago, the first patient is younger than the second patient because there's a numerical difference between the ages of 35 and 60. Or suppose you were told patient A has elevated blood pressure and patient B has normal blood pressure. Based off of this information, you can tell one patient's blood pressure is numerically different from the others. This is an important point. Variables can be quantitative even if you don't know the extent of the difference between the two levels. In the previous example, we were only told there is an ordering of the blood pressure, but not by how much they differed. Qualitative variables, on the other hand, contain no numeric difference between the levels of a variable. You are probably most familiar with this type of data from open-ended survey questions such as, "Tell us about your experience." However, qualitative variables can be more broadly thought of as a variable where levels are categories that are not numerically different from one another. For example, the country you were born in is qualitative because there's no numeric information conveyed about a patient who was born in the United States versus one who was born in Guyana. Other examples of common qualitative variables include which hospital a patient is admitted to, gender, your social security number, hair color, and so on. Variables may be further classified into 4 subcategories: nominal, ordinal, ratio, and interval. Nominal variables are qualitative variables. That is, the levels of nominal variables take on categories that convey no numerical difference or ordering among them. An example of a nominal variable might be what kind of car you drive or what state you live in. Ordinal variables, as the name implies, are variables that contain a rank order between levels of a variable, but not the numeric information. Going back to the blood pressure example from the previous slide, you know that one patient has an elevated blood pressure, which means they have a diastolic reading that is higher than the patient who has a normal blood pressure, but you don't know how much difference in blood pressure is. Other examples of ordinal data include clothing size and order of finish in a race. Ordinal variables are normally considered quantitative variables. Ratio and interval variables are very similar. With both types of variables, you know the order of different levels of the variable, and you know by how much those levels differ. The difference between the two is that interval variables may take on negative values, while the lowest value of a ratio variable is 0. Examples of interval variables include the temperature in Fahrenheit, your golf score, and the amount of money you have in your bank account. All of these examples can have values of 0 or less. Examples of ratio variables include age, height, weight, and blood pressure. Values of 0 for these variables do not make sense. For instance, there's not a person who weighs 0 pounds. Ratio and interval variables are also considered quantitative variables. So why do we classify variables in so many different ways? The answer to this question is that the type of evaluation and analysis we can do on a variable depends on how it is classified. You can do types of analysis on qualitative variables that you can't do on quantitative data, and vice versa. Before we continue on to different ways of describing data, I want to introduce a bit more terminology that is commonly used in data analysis. The first term is raw data. Raw data are data or information that comes to you just as it was collected. Usually, there has been no attempt to filter out useless characters or extra columns or spaces. It is not sorted and may not even be in a sortable format. It may contain extra information that you will not need to answer your questions and may not be useful for your situation until it has been cleaned up. This type of data requires most work in an analysis. Next, we have summary data. This type of data has usually been cleaned up of the extra characters and spaces, and generally an attempt has been made to sort or group the information in some way. A challenge with using summary data is that although it is much easier to work with, you are starting out with data that has been organized based on someone else's goals. This may work either for or against you in your analysis. A data set is simply a collection of various pieces of data or variables. Data sets may contain either raw or summary data. A cohort, generally a group of people that have similar experiences. For example, those of you that take this course with plans to continue on for the certificate can be considered a cohort. Another example of a cohort would be all people who are part of a clinical trial for a new pharmacological therapy. A case is the individual or individual items which make up your data. A case will have several variables describing it. For instance, the case of a patient will have variables describing their weight, height, and gender. A data set is usually made up of several cases. Now that we can define what type of data we have, we're ready to move on to the evaluation step. Statistics provide a useful method for this step. However, what are statistics? To answer that question, we need to define two terms. The first is, what is a population? Put simply, a population is every member in a group that contains a variable that you are interested in. As an example, suppose a variable you are interested in is the systolic blood pressure of all adults in Nebraska. The population, then, that you are interested in is all adults in Nebraska. This brings us to our second term, the distribution of the population data. The distribution of the population data is the collection of all measurements of your variable for every member of the population. So using this example, the distribution of systolic blood pressure readings among the adults in Nebraska is the collection of every resident's systolic blood pressure reading at a given point in time. So this brings us to two definitions of statistics. The first definition is that statistics are a set of methods for describing a population distribution. This is called descriptive statistics. Descriptive statistics allow us to ask questions such as, what is the most common systolic blood pressure reading among Nebraskans? Does systolic blood pressure among Nebraskans differ a lot person to person, or are they relatively the same for all Nebraskans? Is there a relationship between systolic blood pressure of Nebraskans and some other variable, such as weight or diet? The attributes of a population distribution are called a population's parameters. To obtain the parameter of a population, it would require the taking of a census of that population. So for our example, that would mean measuring the blood pressure of every single adult in Nebraska. As you can imagine, this is rarely possible to take a full census of a population, because populations are just too big to measure everyone. What we do instead is measure a sample from the population we are interested in. A sample is just a subsection of your population. For instance, our sample might be the blood pressure of 100 adults who live in Lincoln, Nebraska. The data obtained from the sample has a distribution as well. This is called the distribution of the sample data. We can ask the same questions about the sample data that we did about the population data. The attributes of the sample distribution are called the sample statistics. We use these sample statistics as our best guess of their corresponding population parameter. Let's say the most common systolic blood pressure reading among our sample of adults in Lincoln was 110. Our best guess for the most common blood pressure reading for our entire population, that is, our best guess of the parameter, is 110 as well. The process of making an inference about a population parameter using sample statistics is our second definition of statistics. In fact, this is called inferential statistics. Before we move into descriptive statistics, we need to introduce a few mathematical notations and concepts. Do not worry too much about this. This course will not require you to do very much math yourself. However, it is helpful to be familiar with the notation in order to understand what exactly the formulas that underlie statistics are actually doing. The first bit of notation we are going to discuss is the Greek uppercase letter sigma. Sigma tells us to take the sum of a variable. So let's assume we have the systolic blood pressure readings from 5 patients, and those readings are 72, 65, 67, 72, and 80. We will use X to represent the blood pressure data of the 5 patients. The sum of X, or sigma X, is simply the sum of those 5 values, 72 plus 65 plus 67 plus 72 plus 80, or 356. The notation we are going to introduce is lowercase n, which stands for the length of the variable. This will be called the sample size. In our example, the sample size, where n is equal to 5 for the 5 patients. We also need to touch on the mathematical order of operations. You may remember from your school days, please excuse my dear Aunt Sally, but this is simply the order in which you calculate algebraic functions. The order of operations is parentheses, exponents, multiplication, division, summation, and addition, subtraction. You start by doing any math that occurs inside the parentheses. Then you calculate any exponents, followed by any multiplication or division, followed by summation, and then finishing with any addition or subtraction. As an example, suppose I want you to find the sum of x minus 1 squared for the 5 blood pressure readings. We first subtract 1 from each value because that occurs in the parentheses and that goes first. Then we square each of those values and we finally add them up together, which would give us a value of 57,390. Now we can move into descriptive statistics. Recall, descriptive statistics is the process of describing a population or a sample distribution. A descriptive statistic that describes a population parameter is typically represented using a Greek letter. A descriptive statistic that describes a sample statistic is typically represented using a Roman letter. Remember that samples are drawn from a larger population. This does not mean that a sample statistic and a population parameter will take on the same value. In fact, there will often be differences between a sample statistic and its corresponding population parameter. For example, suppose that the average height of a population of students who takes this course is 68 inches. Let's say that a sample of 50 students is drawn from this population, and the average height of those 50 students is 66 inches. The difference between a population parameter and its sample statistic is called the sampling error. The sampling error in this example would be 2 inches, the difference between 68 and 66 inches. Now that we have defined what statistics are, we can begin the process of describing the distribution of a variable. One of the first questions we want to answer is what value or level of a variable best describes a typical observation in our data set. This can be done by describing the most common value in a data set or by identifying the center of the distribution of a variable. 3 of the most common answers to the above question are the mode, median, and mean. The mode is the most frequently occurring value of a variable. The mode is most appropriate for qualitative variables, but can be used for numeric variables as well. It is possible for the distribution to have more than one mode. This occurs when several levels of the variable occur the same number of times. The median is a measure of the center point of a data set. It is the value for which half observations fall above and half fall below. To calculate the median, first determine the sample size, lowercase n, and then order the data from smallest to largest. If the sample size is odd, the median is the exact middle number. If the sample size is even, the median is a value that is halfway between the 2 points in the center. In the blood pressure example, we would first order our data as 98, 100, 107, 113, and 121. Since our sample size is odd numbered, we pick the middle value and find that the median blood pressure is 107. The median is a useful descriptor of a variable when the data contains extreme values. Suppose the last value of the data set was 150 instead of 121. This extreme value does not affect the median, which is still 107. The mean, or average, is another measure of the center point of the data. You more than likely have encountered this before. The formula for the mean is the sum of x divided by the sample size. Recall from the previous slide, this tells us just to add up all the values of the variable and then just divide by the sample size. To find the mean of our blood pressure variable, we would add 98 to 100 plus 107 plus 113 plus 121, which equals 539. We then divide that value by our sample size to get a mean blood pressure of 107.8. Unlike the median, the mean is influenced by extreme scores. If the last value of 121 was changed to 150, the mean of this data would increase to 113.6. So you have to be careful when extreme scores are present. Knowing how to find the center of a variable is useful, but is of limited value in and of itself. It is also helpful to know how spread out the data are. Suppose we collected 2 samples of patients' heart rate. The first sample had values of 65, 67, 72, 72, and 80. The second sample had heart rates of 50, 60, 72, 79, and 95. Both samples have the exact same mean and median, but the second data are much more spread out than the first. But can we say how much more spread out the second sample is? For qualitative data, we can describe the variability in terms of how many categories the variable contains. But different methods are needed for quantitative data. Two popular measures of variability are the range and the standard deviation. The range is a very simple measure of variability. It is simply the highest value minus the lowest value plus 1. The range is a direct measure of how spread out a variable is. So the range for our first sample is 80 minus 65 plus 1, or 16. And the range for our second sample is 95 minus 50 plus 1, or 46. The range is simple to calculate, but only takes into account two values, and as a result is kind of limited. A more useful measure of variability would include information from every value in the data. The standard deviation does just that. The standard deviation is the average distance of every observation from the mean. So, a standard deviation of 2.5 means that on average, every observation of a variable is 2.5 points away from the mean. Larger values of the standard deviation indicate that the variable is more spread out. The formula for the standard deviation can be seen on this slide for the sample and the population. Luckily, we can use Excel to calculate the standard deviations for us. To this point, we have discussed how we can describe a single variable. Often, it is of interest examining the relationship between two variables. One way to measure the relationship between two quantitative variables is through the Pearson correlation coefficient. The Pearson correlation coefficient is a measure of the degree to which two variables change or covary with one another. It is important to note that this is a measure of linear change. That is, does one variable consistently increase or decrease as the other variable changes? As a simple example, think of the relationship between one's height and weight. As height increases, one's weight generally increases as well. The Pearson correlation coefficient provides a method for quantifying this relationship. The Pearson correlation coefficient ranges between -1 and 1. As the coefficient falls further from 0 towards -1 or 1, the relationship between the two variables is stronger. So for instance, a correlation of -0.75 would indicate a stronger relationship than a correlation of 0.25. Values near 0 indicate that the two variables are not related. The sign of the correlation coefficient, positive or negative, indicates the direction of the relationship. A positive value indicates that their variables increase together, like height and weight. A negative value indicates that as one variable increases, the other variable decreases. The formula for the correlation coefficient is also relatively intense. It is even more complicated than the formula for the standard deviation. Luckily, we can again use Excel to calculate it for us. Now that we can describe the distribution of a variable and measure the degree to which two variables are related, it is helpful to discuss ways in which we can visualize the data. We are going to discuss three commonly used graphs: the bar chart, the histogram, and the scatter plot. Before introducing these graphs, we need to make sure we're familiar with the axes of the graph. The y-axis is the vertical line of the graph, and the x-axis is the horizontal line. Knowing which axis is which will be useful when describing your data. The first graph that we are going to talk about is the bar chart. The bar chart is useful for depicting qualitative data. To construct a bar chart, a label for each level of a variable is placed upon the x-axis. The y-axis provides the frequency for which each level occurs. The bar then represents the frequency of each category with the space between each level. Bar charts are useful for identifying the most commonly occurring category, which you may recall is the mode of a distribution. We can see an example of a bar chart on the slide. The bar chart shows the number of admitted patients to hospitals by location. We can use this bar chart to find the mode of the distribution, which in this chart is Richmond because the largest amount of admitted patients were from there. A histogram is very similar to a bar chart. In fact, a histogram only differs from the bar chart in two ways: the type of variable it is used for and aesthetics. The histogram is most appropriate for quantitative data. Like the bar chart, the levels of the variable are placed on the x-axis, and the frequency or percentage of each variable is placed on the y-axis. One challenge with histograms is setting up the x-axis when the variable has many levels. To solve this problem, we use something called binning. This is done by combining levels of a variable into one unit. For instance, if a variable can range between 1 and 100, we could create bins of 10 in order to plot the variable. The first bin would represent all scores between 1 and 10, the second all between 11 and 20, and so on. Aesthetically, the histogram differs from the bar chart by not placing spaces between the bins of a variable. Like the bar chart, the histogram can be used to find the mode of a distribution. This is simply the highest point on the histogram. A few slides ago, I mentioned that the mode may be used to describe the shape of a distribution. When a distribution has a single mode, it is called a unimodal distribution. When it has two modes, it is called bimodal. If a distribution has no mode, that is, every value of a variable occurs an equal number of times, the distribution is called uniform. A distribution that is unimodal and symmetric around the mean is called a normal distribution. This distribution will be very important in the course. A normal distribution has a mean, median, and mode that are equal to one another. Below, on this slide, we can see the histogram of the resting heart rate of 1,000 patients. This is an example of a normal distribution. It has a single mode of around 80 and is symmetric. The mean of this data is 79.98, which is very close to what the mode is. The bar chart and the histogram are useful for visualizing a single variable. But what if we want to see two variables simultaneously? The scatter plot is a useful way to visualize the relationship between two quantitative variables. To construct a scatter plot, one variable is placed on the x-axis and the other is placed on the y-axis. For example, we might place height on the x-axis and weight on the y-axis. For now, it doesn't matter which variable you place on either axis. In the body of the graph, we plot the points which correspond to the values of both variables. The scatter plot is particularly useful when visualizing the correlation between two variables. The graph furthest to the left shows the relationship between height and weight. This displays a strong positive correlation. Notice how the data points form almost a straight line. The central graph shows the relationship between the amount of exercise and weight. This shows a weak negative correlation. The third graph shows the relationship between age and height. Not surprisingly, this results in a correlation close to 0. And this brings us to the end of this week's module. For the homework, it will be necessary for you to review the document on using Excel to compute descriptive statistics. Additionally, I posted documents on creating a memo that should help you with the homework. Coming up next week, we will discuss various ways you can approach a research topic, how to establish cause and effect, and various threats in interpreting your results. If you have any questions on this week's topic, please do not hesitate to contact me, and I will respond the first chance I get.